So what I have prepared now for the next, well, let's see how long it takes, is no new content, obviously, but a quick summary of everything we've gone through, or at least the highlights, the main ideas, from like not the highlights from like novel ideas perspective, but like the foundational stuff that I've covered over the last 24 lectures. And I'll try and go through that. But you can also stop me at any point in time with questions, right? So I don't even mind if you don't make it through all of the slides, something like 20 odd. So yeah, but that's okay. So let me begin. We started in lecture 1 with the laws of probability, which all of you have encountered in previous lectures before. And I've already written it down here on this slide, copied over the content from the lecture number 2, where I introduced probability densities as representations of probabilities over continuous spaces as the natural object which takes on the structure that we also have in discrete probabilities, namely the two main rules of probability theory, the sum rule and the product rule. This is the rule for getting rid of something you don't know, and this is the rule for conditioning on something you do know, and then talking about the stuff you don't know. The two of them taken together amount to Bayes' theorem, which is the fundamental rule for inference everywhere, not just in science, but literally everywhere. By the way, when I walked in here, I saw a sheet here that's from my colleague Martin Butz for cognitive architectures. And it's his cheat sheet that he hands out to the students, the Formelsammlung. And it actually contains Bayes' theorem as well, and then variations of it. So cognitive science, clearly also an application field. For continuous probability distributions, we have to be a bit careful. There's this minor thing that somewhat annoyingly complicates life, that if you rescale the domain over which you assign a probability, then you have to make sure that density is correctly corrected by multiplying with the determinant of the Jacobian of the transformation. Okay, so that's the fundamental rule. That's just a philosophical statement about how to reason in a situation where your information sources, your data, does not fully provide the knowledge about the variable x that you'd like to know. But unfortunately, these abstract statements, which are sort of manipulations of functions or functionals, are effectively intractable for the general case. If you have a general function for every term in here, if that's a general distribution, some general probability distribution that just sums to 1 for z and for x, then this object here, well, you can multiply it pointwise, but even the integral is difficult to evaluate in the normalization constant. One way to think about this is that if you have a discrete probability distribution, then the number of possible states that you have to consider here is all the possible combinations of these discrete variables. Let's say they are binary random variables, then the number of configurations to consider grows as 2 to the number of variables, right? So in this case, it's if x and z are both binary, we already have 2 to the 2, 4. And if you had 3, 4, 5, 6 variables, then the complexity of this inference process would exponentially grow with the dimensionality of the problem. And so the entire course from lecture 3 onwards was all about making things tractable, to reduce computational complexity, so that we don't have to consider the combinatorial set of possible hypotheses, which obviously is not possible for continuous spaces in any case. And the key tool for this were Gaussian distributions. If all variables in a generative model are jointly Gaussian distributed and linearly related to each other, then inference maps to linear algebra. And I wrote down these initially cryptic equations, which by now I hope you have developed an eye for. So if you have a prior distribution over a latent quantity x and observe data y with a Gaussian likelihood that links the data linearly to x, then both the evidence and the posterior are closed form expressions, Gaussian distributions, Gaussians are parameterized by a mean and a covariance, a vector and a matrix, and that this vector and matrix, this point estimate and uncertainty estimate, have an interesting structure that, though it's a long formula, amounts to linear algebra. You have to build some matrices and then solve a linear system of equation that we tend to write with an inverse on a matrix multiplied with the vector. But as we learned, you should really be thinking about this as like this joint object, inverse matrix times vector, as another vector that solves a linear system of equations. And we learned about how to interpret these quantities. So this object here, this gram matrix, is the expected variance of y under the prior, actually of y minus the mean prediction. This is what you thought you would see. It's your best guess for what you're going to see. This is what you did see. This is the residual between the two. This is the scale on which you expect this thing to vary. So this times this gives us some kind of innovation, how surprised we are about the data we got to see, and then we project this, push this towards the variable that we actually care about, because this quantity is the covariance between this object and x. Similarly, the posterior covariance also has this sort of update form that looks a bit like a Schur complement. There is an initial covariance, prior covariance, and then a correction which involves the same matrix inverse that's in here as well. And this means that adding uncertainty in Gaussian models doesn't increase computational cost, because you can reuse computational effort used to find the mean estimate. That's a first insight that sometimes being probabilistic, having uncertainty, doesn't actually have to have cost overhead. We also noticed that this is, I'm going to talk about that in a second. So then we talked about, actually in the next lecture, I then talked quite at length. I made you sit through a long lecture about linear algebra, the tools we use to solve problems of this form. And we discovered that there's actually nothing new hidden underneath this linear problem, because it's just more instances of Gaussian inference. The path to that was to discover, or kind of mentally do this exercise, that we could, maybe an underlying structure is actually that a model like this is of an exchangeable nature, in the sense that I can start with the first entry in y, the very first datum, condition on it, and then because of this equation, I get back a new Gaussian that I can then condition on the next datum, one after the other. So Gaussian inference is a form of closure. You start with a Gaussian, you get a Gaussian data point, you get back a Gaussian. That means we can split up our data set into individual terms, scalar observations, one after the other. And if we do that, then these inverses here are just scalar inverses. And we never need to call some fancy numerical linear algebra code, at least in principle. It's still probably a good idea to do this if you have a decent sized data set. But in the corner cases of very large data sets, and sometimes also very small data sets, it can be useful to realize that the algorithms we tend to use to solve such linear systems of equations, something like this, so an algorithm that consists of a matrix decomposition first, that returns a solver-like object, a function that we can call on right-hand sides. Algorithms like this are just methods that do Gaussian inference in a sequential fashion. For example, this is true for the QR decomposition, for the LU decomposition, for the Cholesky decomposition, for conjugate gradients, for preconditioned conjugate gradients, for Lanczos algorithms for the decomposition of matrices into SVDs, and so on and so on and so on. All of these algorithms iteratively project, that's this policy up here, the rows or columns of our matrix A or A transpose onto another, onto the current posterior of a Gaussian distribution to construct a set of conjugate directions U using the Gram-Schmidt process or modifications thereof to construct basically a data structure in memory that is either numerically stable, in the case of methods like the QR decomposition, LU, and Cholesky. And so there the policy is chosen such that everything like neatly aligns and there is very little overlap between the directions. Or they choose the direction such that they provide maximal information about some right-hand side B, or about the solution for some right-hand side B, as in the case of conjugate gradient or Lanczos iterations or so on, at the cost of numerical stability then, but at an increased gain in convergence. Why was this useful? Well, it's one direct, tangible outcome of this is that we can actually think of linear algebra methods as a form of data loader in the Gaussian case. They allow us to pick informative views onto the data set. And that then might mean that we don't have to load the entire data set. We can stop the computation after some, well, reasonably short computational effort compared to solving the full problem, and then stop the computation and provide an uncertainty as an output of this method that actually takes the fact that we've only loaded parts of the data into account, rather than guessing what the uncertainty should be. So over the course of these lectures, 1, 2, 3, 4, actually, no, 3, 4, and then also 5, we kept building a software library along the side that I don't have on the slides that implements this Gaussian mechanism in a abstract data class, effectively, with a bunch of methods. And I did this just a second on purpose to highlight that these Gaussians come with all this functionality, and as soon as you know something is Gaussian, you can apply all of these mechanisms directly. Now there's your question.
I have a question. Is the pathway you say that it's a data loader where you choose the best learning data points directly related to the fact that you can stop? Or is that two benefits that are just go well together?
Okay. So that's a good question. The question is, I said something about being able to stop early and about thinking about a data loader and how are the two related to each other. I would say, I mean, the reason to stop early is that you think that you've learned enough, right? So in principle, maybe the formal statement is any of these solvers of this form can be stopped at any point in time, including after 0 iterations, then you just get back the prior. This is, for example, also true for the QR decomposition or Cholesky decomposition. And this is maybe useful to point out on its own, because in numerical math lectures, you will typically hear about methods like the Cholesky decomposition, the QR decomposition, as so-called direct algorithms. So people will say that these are methods you have to call, and then you have to stand back and wait for a cubic amount of time, and then they'll give back the true solution. But in fact, you can stop these methods early. It's just that they tend to have, on average, in the average case, a very slow convergence. There isn't really a reason to expect them to converge quickly. And so that's probably why people want to wait for them to complete. In fact, there's a theorem, if you really want to read up on this, it's unrelated to the exam though, it's actually in the appendix of the Hesteles and Stiefel paper from 1950 odd something, which introduces the conjugate gradient method. So the inventors of the conjugate gradient method, they pointed out that conjugate gradient was necessary because these methods converge slowly, and they have some worst case construction showing that if you run one of these direct methods like QR or LU or Cholesky decompositions, then you can pick linear systems of equations such that the error on like this mean that comes out of this method increases in every single step of the method. It gets worse and worse and worse all the time until the very end. And then in the very last step, everything converges and you get a perfect correct answer. And that's not true for these more iterative methods like conjugate gradient and Lanczos SVDs and so on and so on. And so therefore, people tend to think about this as different things, right? Or actually maybe also as connected things. So if you have methods that tend to not be good for a long time, then why run them only for a short amount of time? But if you think of these methods as quantifying uncertainty, then it becomes maybe more natural to think about them as stoppable at any time, because then what's going to happen in a situation where the algorithm just doesn't learn anything from all the iterations is that the uncertainty won't collapse either. So you'll just have a big error bar that just stays pretty much almost constant for a very long time and then suddenly collapses to 0. Yeah. So if you have a data loader that is useless, that always loads the worst, least informative data, then maybe it's not a good policy to stop early. But if you happen to have a data loader that is very efficient at loading the right data, then you might want to stop early. And conjugate gradient for linear Gaussian problems is an example of a very efficient data loader. So what do we do with these tools? Also with the software tools that we developed, they became the foundational framework for maybe the most important task in machine learning, even to this day, at least as an abstract task, namely learning functions, regression. We initially looked at real-valued functions, where we began with a traditional classic perspective on parametric regression. So the assumption is we have a supervised machine learning problem. There will be pairs of inputs x and outputs y. We make an assumption that the function that links x to y has a parametric form. It is given by some features of the x, so a function phi evaluated on the data x, weighted with some unknown weight vector w. That's a generic formalism. This phi of x we could maybe also think of as a deep neural network, or we could just think of it as a bunch of features you pick by hand. Then, in such a situation, the important key observation here is that the weights enter linearly in this problem. This may well be a very nonlinear function of x, but it's a linear function of w, and that means we can directly, without changes, apply this Gaussian formalism. We put a Gaussian prior over the weights. That implies, by the way, by some of the properties of Gaussians, also a Gaussian prior over the function values. Then we use a Gaussian likelihood for the observations, so that makes the two key assumptions, Gauss and linear relationship. Then we can look up everything that was on the previous slides and find that the posterior over the weights, given the data, is a Gaussian, which involves these linear algebra expressions for which we can use these linear algebra routines. Question. Yes, that's actually a very good observation. It's a standard assumption in regression to say that the noise on each datum is always the same, and also the data are independent of each other. So technically, for what's here on the slide, this is not necessary. You could have a joint complicated covariance matrix here, so a full let's say there are n data points. It could be a full n by n symmetric positive definite matrix. Such a model has the fancy name a heteroscedastic problem, so one that has different noise on every datum, and in fact the data points are related to each other. So in textbooks, you tend to see this assumption with a scalar noise. So the reason for this, I think, is so there are certainly applications of regression where you actually have to model different noise on every datum. There are very few reasons why you might computationally have to use something like this, a structure like this. It's still very common. So maybe one first observation is that if we had data that has a joint full rank non-diagonal covariance, then we could use a singular value decomposition of the covariance matrix to project our data set Y onto a new data set that is independent of each other, at least, right, with independent observations. Those would then still have a diagonal covariance, but we could rescale the observations so that they have a scalar covariance. So in some sense, this is not a strict restriction because you can take any data set and remap it such that it has this form. but then it might lose a lot of the physical interpretation, right? Not necessarily measurement anymore. The other thing is that it's, I mean, in statistics, not in probability theory, but in statistics, the IID assumption is like very fundamental. So the assumption that you get a lot of data of the same type, IID, from some source. That's important to make, you know, all sorts of theoretical analysis, to show convergence rates, the stuff you heard from Matthias Hein across the corridor. And so this amounts to this making this assumption, that all the data are distributed independently of each other. That's what the 1 stands for. And that they have the same distribution. That's what a constant sigma stands for. Okay, so if we do this, then we get a framework with which we can learn functions. And we spoke about these models for quite a while. I highlighted that you're very free to pick the features here. This feature set phi can be literally anything you want to pick, including functions that are discontinuous, even including functions that are technically unbounded. I mean, you could even have a framework where some of these phis return nons or infinities. Then you have to be a bit careful about how you implement the inference, but it's still possible to do this like correctly. That's simultaneously maybe a blessing and a curse. It means you get, if you really know something about your problem, you can build very powerful, very well designed, constructed algorithms. For example, I know of applications, some of them are published, in major companies where engineers invested a large amount of time finding good features. So for a while, a common example that people talked about in the community like a decade or so ago was when Facebook became big. They hired several people out of another company who became, for example, Joaquin Coñonera Candela, who was from Tübingen as a postdoc originally, and then he became the head of AI at Facebook. And he built a massive tool for ad placement on Facebook, which some of you may have suffered through because you were the subjects of it, right, if you were ever on Facebook. So it's the algorithm that decided which ads to show. And to get that to work, he had a big team of engineers, and they built a software platform that allowed the engineers to trial features. So they could provide a new example phi, something like, I don't know, I'm looking for customers who recently announced their wedding on Facebook, right? There was some type of, like, I don't know, some way of posting that, because that probably means you're gonna buy some very special stuff, right? Or something about babies, or about changing your relationship status, and so on. And they had a tool for people to trial these features. So they could get like 1% of the population as an A/B test setup, and then they would continuously compute the evidence. Where is it? It's going to be on the next slide, one afterwards. But it's actually, I mean, it's basically this expression up here, right, where the A's now include the phi's. Check how well this works as a predictive performance tool for whether people would click on some ad. And if it worked well, it would automatically load those features and add them in. That was pre-deep learning. But it was an approach that scaled to very large user bases. You could do that with a few 100 million people because you get to like, manually design this kind of process. But of course, it's also like sort of disappointing as a designer if you want to build a learning machine, something that automatically decides how to like best extract information from a data set, if you then have to sit down and manually decide how this machine should do this. And so people in machine learning have spent, well, one of the like main trends basically, including deep learning, is the attempt to automate this process in various ways. And so over several lectures, we discussed how to automate that process. A first very powerful and historically maybe for a while very successful approach was to say, what happens if we increase the number of features towards some asymptotic limit of infinitely many features in some sense? We have to be very careful, of course, how we do this limit process of infinitely many features. We did this. We discovered that there is this, basically it's on the previous slide, right? There's this interesting structure here that to compute these predictive distributions, at least if we think about them as function values, then there will never be a lonely phi in this expression. So if you make predictions not about the w's but about the function values, then you'll get here a phi sigma phi, phi sigma phi, phi sigma phi expression, and up here as well, phi sigma phi. They are always inner products. So inner products are sums, and some sums even work if they have infinitely many terms, because they have analytic expressions that don't require you to actually go through the sum. You already know this from introductory math lectures about series. And that led to the idea of kernel machines, algorithms which replace these inner products with functions that can directly be thought of as evaluations of inner products in infinite dimensional, in general, feature spaces. And the associated notion in probability theory is that of a Gaussian process, a non-parametric model that has in some sense an infinite number of degrees of freedom that it can fit to a data set. So Gaussian processes, I removed the code here, from a computational perspective can be thought of as a lazy evaluation of a Gaussian model. So you write a piece of code that basically waits until it is given a data set, and once it's given this data set, that's a finite data set, it constructs a finite matrix, a kernel-Graham matrix. That's this matrix here, or actually it's this whole thing, solves this finite system of equations, linear system of equations, and then stores the resulting values, which are a vector of finite length, and the matrix decomposition of this covariance, which is some matrix decomposition of finite size, might be, for example, a Cholesky or something else updated using the algorithms that we've encountered before, and then provides access to a function, a kernel, and a mean function over here, which can then basically act as a closure for a new Gaussian process. We studied these algorithms for quite a while. We discovered that they had very interesting properties. For example, we did an example for constructing a Gaussian process prediction on a very relatively simple but structured one-dimensional data set, this Keeling curve of CO2 curves. We discovered that you can actually use different kernels. There's a few kernels, and in fact, there's some kind of standard set of kernels from which people tend to choose. Things like the Matern kernel, periodic kernels, the Matern family of kernels, which includes as a limit case the square exponential, a very common kernel that is in some sense quite deeply flawed, but also the Wiener process, integrated Wiener process, and so on. And actually, there is more than just this finite collection of kernels, because you can construct new kernels from old through these four properties of kernels. So scaling a kernel gives back a kernel, transforming the inputs of a kernel in an arbitrary fashion, as long as you apply the same transformation to both inputs, gives back a kernel. Adding kernels gives a kernel, and multiplying kernels gives a kernel. So they form, if you like, a semi-ring of bivariate functions that are all positive definite. And these properties can be used to, again, build maybe more flexible models than we had for the parametric form. But again, a relatively expressive language in which designers and engineers can encode knowledge about specific problems that they are trying to address. And I find it very important to point this property out, because people who try out Gaussian process models for the very first time on a particular data set tend to think of them as some kind of black box. The standard setting is that someone gives you some data set in a professional environment, so you open up some SciPy or scikit-learn, implementation of Gaussian process regression that uses some standard kernel, don't think about it, and then it doesn't work particularly well, because the standard kernel, which is usually a Gaussian kernel, is not a good choice. And then people say, oh, so I tried a Gaussian process, it didn't quite work so well, so I did something else. And then they spend a lot more time trying to fit some large deep learning model, and because they get invested in it, then make it work. So methods like this still work well on many data sets if you are careful to design them right. A part of this process of designing them right is to pick smart kernels that describe what you are trying to do. If the data set is sufficiently low dimensional, then this can be checked by plotting prior means and variances and samples from the prior. But then you're typically also left with a bunch of parameters in these models. So parameters here could be length scales of kernels or the individual strengths of individual components in sums of kernels. And I pointed out in the lecture on the example for how to build Gaussian process models that such parameters can be learned in Gaussian models. And that's actually a first instance of a quite generic framework, which is maybe at the boundary between probabilistic/Bayesian inference and more statistical analysis, namely marginal likelihood estimation or maximum type 2 maximum likelihood estimation. This uses the insight that in Bayes' theorem, the normalization constant, the evidence, this thing down here, can be thought of as, well, that's actually what the term evidence is supposed to highlight, can be thought of as a likelihood, not for the latent quantity that we're trying to compute, that's up here, but a likelihood of higher order for the model, the generative model over the latent quantity and the data. So in this case, for theta. And so just like we can use this first order likelihood and its prior to compute a posterior over f, we can use this likelihood to in a mechanism to estimate theta. Typically, this likelihood will not be of Gaussian form, and it might not even be tractable in general models, but for Gaussians it is. But then we can try to find maximum likelihood estimates or maximum a posteriori estimates by multiplying with a prior for theta. For Gaussians, this happens to have analytic form. So one of the properties of Gaussian distributions is that the evidence, this distribution over y given only the model, and we marginalize out the f, the unknown function or the unknown weights, actually is itself of an analytic form. Where analytic form here means it's the expression of a Gaussian probability density function for y, evaluated at some mean and some covariance that is a function of theta. So as a function of theta, if you think of this as a likelihood, it's not a Gaussian function, in contrast to the weights for the linear model. But it's a function that we can analytically evaluate for any value of theta. And that means we can optimize for it. So we can write down in particular the logarithm of this probability distribution, which is this expression, has a very specific form. It involves this square error, weighted square error, and then a complexity penalty, something that rises with the determinant of the covariance matrix, which is a measure of entropy. So like how much volume is in your space of hypotheses, how many hypotheses you're entertaining. And this expression as a function of theta, we can implement today, at least in automatic differentiation frameworks, feed into an optimizer, and then optimize. If our model for the function in here and in here contains features that we can sort of parameterize in the form of a differentiable program, like a deep neural network, then this is actually one way of learning a deep neural network. And you can tell that it's slightly different from the standard way of learning deep neural networks, which only involves this term, but not this term. For that, we just need to be able to get this log determinant. So that was the generic framework for learning functions. And then one of the things we discovered is that if this framework, at least if you implement it using numerical linear algebra rather than stochastic gradient descent, it tends to be expensive because the size of this matrix in here grows linearly with the number of data. So if y is of length n, then this matrix is of size n by n. And that means, at least in the worst case, if you want to build a user matrix decomposition of these direct forms that I mentioned before, then the cost of constructing this solution will grow cubically with the number of data points. That's in contrast to the parametric form, this one, where there is a matrix in here. At least there's one way of writing this problem that constructs a matrix that is of constant shape whose size is given by the number of features we are considering. And so that matrix only contains terms in here that involve a sum over the features. So that means that sum grows quadratically with the number of data points, but the overall, like this inversion problem here, stays constant over time. It's always cubic in the number of features. So this is a reason why people used to argue that Gaussian process models don't quite work for very large data sets. This has changed a little bit with the advent of better numerical linear algebra. There are now tools like GPyTorch that allow Gaussian process inference for up to like 1 million data points, maybe. Not for like internet-sized data, but already quite large. Nevertheless, there are some data sets that are just even larger. In fact, there are some data sets that are effectively infinitely large. That's the setting for online learning, where you're sitting in front of a data source that continuously spits data points at the algorithm. For such settings, which are also known as time series, we need algorithms that have a complexity, computational complexity that is constant per datum, which means it's linear in the size of the data set. And it turns out that the Gaussian linear case actually has a special variant designed for such settings, which also builds the foundation for inference in time series. And such models are called Markov chains or Markovian models. They make the assumption that the dynamics of the data set can be described in terms of some state space that contains variables x. It has the property, so being a state space means that everything that happens into the future is conditionally independent of the past if you know the state. That's what this Markov property says up here. And then if we additionally make the assumption that our observations at any point in time only depend on the state, only on the local state of the system, then that's this additional observation. Then we found, through some quite tedious derivation, that in such settings, there is a generic algorithmic structure for which we don't have to make further assumptions about the shape of the probability distributions that provides a local predictive update. So you can locally predict the future from the past. That's called the Chapman-Kolmogorov equation. It has this particular form. It's effectively a recursion. Then a local update using Bayes' theorem. And those two together are the algorithm for continuous prediction in time series. And there's a special setting, which is sometimes confusing because it's, like I also did, tends to be taught alongside the prediction update loop, which is that if you happen to have a finite data set of some long length, then once you're at the end of the data set and there's no more future to come, you might want to start considering what happened in the past and reconsider your old predictions in light of what happened later. And that involves a process of passing backwards through time, which is called smoothing. Smoothing really only makes sense if the data set is finite, because otherwise we end up with a quadratic cost, a superlinear cost in time. All right? So because as we get more data points, we have to send messages backwards through time to ever more data points, and that doesn't scale. But the forward prediction is always linear in time. Yes?
What speaks against doing a window-wise recursion if you're doing real-time processing?
Yes. So the question is, why don't I do this in a windowed fashion? Yes, you can absolutely do that. So if you have like a tail of the last B observations that you drag behind you, you can always do a smoothing pass with a limit towards B, right? So you say I'm dragging the last B observations behind me for which I want to have smoothed observations. And then that's, I think, well, if you want to be sort of mathematician about that, you could say that's like making the state space larger, and then you're again just filtering and not smoothing. Like you're like increasing the size of the state space by size B, basically. Or, yeah, it's just not So the point of smoothing is that afterwards you get a consistent posterior that amounts to a joint distribution over all the states. And that you don't get in a windowed fashion, right? That sort of breaks this idea. So, here's another slide that doesn't help much, that just shows that these forward-backward loops exist. And so that's, again, an abstract statement. We actually also discovered that this abstract structure can be, like, there's a very efficient, like, interesting structure to it. So this update here, actually the joint of these two, so first this, then this, if you write this as one equation, happens to have the property of an associative scan of associative, what's the word for that? The other word? Well, it's an associative scan. That's that one technical term for it. And that means on parallel hardware, if you have a finitely long data set, the cost of this can actually be dropped to logarithmic complexity in the length of the data set, the time series, assuming you have an unbounded number of compute threads available. But that was just like an interesting side observation because it's a relatively new observation that only begins to be used now in implementations. And then now the final thing I want to say about these Markov models is that, of course, these are, again, abstract. This is just abstract equations, so it's in some sense not particularly concrete. But if we, again, make Gaussian linear assumptions, so if we assume that these three distributions that we need to define the Markov chain, the initial distribution, the predictive distribution, and the observation model, if those are all linear Gaussian, so if they're all of Gaussian form, and the relationships between variables involve linear maps, and the names of these variables have canonical meaning, then we arrive at a tractable algorithm that is the foundation of signal processing, called the Kalman filter, and the associated smoother is called the Rauchtung-Striebel smoother. And they have very classic forms. It can be written like this for the smoother, like this for the filter. This is not the only way to write them. There are other ways of writing them, for example, in terms of the inverse covariance, that's called information form, or the update here can be written in a slightly different way, but they all end up being the same algorithm. And that algorithm can be used, that class of algorithms can be used in a very general set of applications of things changing across time, basically. Which includes the modeling of dynamical systems. If relationships between such variables across time are not Gaussian and not linear, then what people in this signal processing community, the original, like the foundations of control theory and rocket science and so on, which are very, very well studied, what they then tend to do largely is to linearize in some form or another. So to project back from the nonlinear shape onto an instance of Kalman filter and smoother, where we now basically create maps from the nonlinear model to these particular parameters, to A and Q and H and R. This, as I pointed out, actually includes, interestingly, a large class of solvers, simulation methods for dynamical systems driven by ordinary and partial differential equations. So solvers for ODEs actually can be thought of as Kalman filters. The connection is particularly precise for one class of ODE solvers. They're called Nord-Seek methods, but actually the majority of ODE solvers are in some form, like sometimes more, sometimes less direct instances of Kalman filters, including Runge-Kutta methods and other methods that you may have encountered in numerical analysis classes. That's useful because it allows us to connect information from empirical data, observations Y, and information from mechanisms, knowing that the system follows a differential equation jointly. Now we're halfway through the term, and I'm also halfway through the lecture, so now I could take a break, unless someone wants to ask a question. No, there's no question. So this was the Gaussian part of the course. And then after the break, we're going to swap to the approximate non-Gaussian part of the course. So this was the roughly first half of the term and of the course. I remember that back then you kind of, it felt to me like you were getting a bit antsy about all this Gaussian stuff. It's like, when are we going to move away from Gaussians? I understand this. I also hope that now in hindsight, now that we are at the end of term, you may understand why I hammered on so much about Gaussians. The reason is that as an underlying structure, mapping inference to linear algebra, they stayed with us, of course, for the rest of term. And whenever we did something that's non-Gaussian, we ended up somehow mapping it back to Gaussians, because then things become tractable again. And we started this journey very explicitly trying to expand away from Gaussians. And said, what kind of, if we allow ourselves, like knowing that we can't allow general form probability distributions over continuous spaces, because they give intractable posteriors, is there something larger, a more powerful general class than just the Gaussians, the parametrized family of distributions that have a mean and a covariance in this sense? Beyond that, that still allow us to do something tractable. And we arrived at this concept of an exponential family. An exponential family is a family of probability distributions that can be parameterized by a set of parameters W and has this form. So, and this is at first, again, a bit confusing or like something you have to stare at for a long time, but actually every expression in here has a very specific role. So this is a probability distribution that is the exponential of, that gives us the name, an inner product between something that only depends on x and the parameters W. So this is clearly linear in the parameters. Those things that are nonlinear in x and only evaluate x are called the sufficient statistics. Then a function that gives us, that ensures that this expression is, when you integrate over x, is equal to 1, so a normalization constant, a log normalization constant, called the log partition function, because it's not actually a constant in terms of w, it's a function of w, but it's a constant in terms of x, plus a base measure, something that doesn't involve w, but just kind of gets added on literally. So sufficient statistics, natural parameters, log partition function, and carrier measure or base measure are names for this. So we, the first thing for which I don't have a slide that we discovered is that many of the classic distributions you will have encountered in a statistics class, like the Bernoulli, the beta, the Dirichlet, the gamma, the exponential, the Laplace distribution, the Gumbel distribution, the Gompertz distribution, whatever, all of these distributions that you have encountered in stats classes are of this form, including the Gaussian, actually. And they just have different sufficient statistics and associated natural parameters. So that's maybe interesting, but why is this? Well, in a sort of backhanded way, we discovered that this particular algebraic structure engenders some really useful functionality. The first one is that all exponential families have a conjugate prior. So they allow us the construction of a closure from the computer science perspective. So where there is another distribution, so for an exponential family over the variable x, given parameters w, there is another distribution over w with new parameters, alpha and nu, which is also an exponential family. It just has different, very specific sufficient statistics and a potentially unknown log partition function, such that when you multiply these two together as a function of w, so that's what you do in Bayesian inference, you get another function of w that has the same algebraic form. So it's another member of this exponential family. So making observations, the process of Bayesian inference is an operation under which this exponential family is closed when Bayesian inference is identified by this likelihood. And in particular, we can also make predictions about future data points by marginalizing over the data using the structure of exponential families. And we discovered that what we have to do is to effectively evaluate a difference between two log partition functions of the conjugate prior. So that means that exponential families endow every exponential family endows a conjugate prior that spans a space of probability distributions that are closed under observations with our original exponential family as the likelihood. That's powerful because it means that there is some kind of structured space of distributions in which we can do efficient inference. And what does efficient mean? It means that we just add up sufficient statistics and count how many observations we've seen. That's the operation we need to do. And that's also why the word sufficient statistics arises. That's what we need to do inference, right? Those are the only things we need to store, is the number of observations and their sufficient statistics, which is a constant in-memory operation. But on top of that, oh, yeah? So you think, can't the sufficient statistics be arbitrarily complicated? Well, so the sufficient statistics are identified by the original likelihood, right? So they're in here. And so they remain as complicated as we choose them in the original likelihood. So if this is a Gaussian, for example, with Gaussians are an exponential family, then this phi of x is x and xx transpose. So the empirical mean and empirical covariance, if you like, up to normalization. And then that's the stuff you need to store. If it's a categorical distribution, then the conjugate prior is a Dirichlet, and phi of x is literally just x. So that is easy. But of course, you can think of other exponential families for which this might be harder. And in fact, we encountered some in deep learning later on, in the instance of linear models, where this object is also completely intractable. So in addition to full Bayesian inference as a closure, in exponential families, we get even more. We get all sorts of properties of the distribution that are commonly of interest in information theory, information geometry, statistics, like expected values of the sufficient statistics, like the Fisher information matrix, like the entropy of the distribution, the cross entropy between two members of the exponential family, Kullback-Leibler divergences between the two members of a family, the score, the expected score, and so on and so on. We get all of these in terms of derivatives of sometimes higher order of the log partition function, up to the base measure, and the base measure, the carrier measure might be 0, and then that doesn't matter at all. So these things here on the left, they tend to be integrals, so they tend to involve expected values. But we can evaluate them without doing integrals using automatic differentiation of the log partition function. So I sort of quipped back then that if you have an exponential family, you could write a generator for the Wikipedia article that populates all the fields of the Wikipedia article for your probability distribution by using these properties. Basically, symbolic differentiation of a log partition function tells you everything you need to know. And this may be historically the reason where all of these distributions came from, because the people who invented them needed to do Bayesian inference. Whether they called it that way or not doesn't matter. They needed to do Bayesian inference or at least map estimation and then quantifying confidence using all of these properties. And so they ended up with probability distributions in which they could do these computations efficiently using, derivatives of the log partition function. But that's only true if we have the log partition function. So a positive way of reading this is if someone gives you one integral, the partition function, which is effectively an integral, then you can get everything here for free. But the other way around, you could also say, to get all of this, you need to be able to integrate over the sufficient statistics. And so what happens if we're encountering models in which that are maybe probability distributions of some form that can be thought of as linear in some parameters, but nonlinear in the inputs, such that this object, which is given by, let me go back, again, like the logarithm of this integral is not tractable. And such a situation arises, for example, in machine learning, in supervised machine learning, if we do classification or regression with a general linear model. So we have inputs x, of which we evaluate some features that we have either manually chosen or that an optimizer picked for us by parameterizing these features and then following some gradient descent routine or some optimization routine, so that we get a general set of features here. And we can't compute this normalization constant then. So for that, we needed our first instance of an approximate inference method. And the one that I proposed, which is maybe the most daring, but also the fastest and maybe most general approach, is a Laplace approximation. So that's the very first tool in your toolbox for approximate inference, which is based on a differential analysis of a probability distribution. With the differential, I mean that it's a local description of the distribution in terms of a point and its geometry, gradients, Hessians, Jacobians around that point, or evaluated at that point. And this works as follows. So consider any model that amounts to like where you find an estimate of the parameters through some form of empirical risk minimization. That might involve a regularizer, or it might not involve a regularizer. Here's the equation that I used for the deep learning lecture, which is an instance of empirical risk minimization. But we could think of the very same situation for exponential families. That we take a logarithm of an exponential family, there will be a phi of x and then a w in here. So now theta is equal to w, and then this regularizer might amount to this conjugate prior, right, which is another function of w that is here. And now we need to find a posterior over theta. We first realize that typically this minimization problem that we write down here actually is a log posterior. So for deep learning, for example, these loss functions that people tend to use are, for example, the L2 loss or the log loss, cross entropy. These are all instances of logarithms of likelihoods, categorical likelihoods, Gaussian likelihoods. And these regularizers that people tend to use, like L2, are logarithms of other distributions, for example, Gaussians. And so we can think of this expression as a unnormalized log posterior distribution. And now what we can do to get an approximation to the associated posterior is we find a mode of this loss, so a minimizer or a maximizer, depending on whether we put a minus in or not, we either maximize or minimize, to find a theta star. That's our point estimate. And then at this point, we do a second order approximation of the loss. I should have moved the slide a second earlier. So this is actually what I just said. So consider a loss which you know to be a log posterior, or maybe a negative log posterior. Then find a minimizer of this loss at this point in the loss. Like that's a minimizer is a point where the gradient is 0. Do a Taylor expansion to second order. We assume that we can do that because the loss is sufficiently regular. So that's the only constraint we actually have. We have to assume that this thing exists, that we have found a point where the gradient is 0, so there is a mode, and then at that point, we can evaluate this object, so that's the second derivative of the loss, the Hessian in general. Then, if we look at this expression, we see that it's a quadratic form. There's no linear term because the gradient is 0, and there's a constant term in front. We have deliberately dropped higher order terms. There's like a decision that we take to drop these higher order terms. And then since we know that this expression, this on the left-hand side, is the logarithm of a posterior, then that means the posterior is the exponential of, minus this expression. So then on the right-hand side, if you do the same thing, if you take an exponential of this, we get a constant, and then times e to the minus 1/2 quadratic form. And that we can identify with a Gaussian distribution, centered at the mode with, okay, yeah, I copied that over, that's not good. So this is obviously the inverse of this, the inverse of the Hessian. And now, there we go, we have a Gaussian. And we get a Gaussian distribution purely using differentiation. There's no integrals being solved, no random numbers being drawn, no fanciful partial evaluation of some integral, as we're going to have in a second, but instead just automatic differentiation paired with optimization and linear algebra, which are tools that are commonly available in across machine learning, differentiable programming, including deep learning. So Laplace approximations are a nearly universal tool to construct a Gaussian posterior on anything, including on exponential families, but also on entire deep neural networks. And then I did these 1 or 2 or 3 lectures on how to apply this mechanism to deep neural networks as maybe the most direct bridge from the classic theory of probabilistic machine learning to the more modern, or currently more prominent, more hyped dimension of differentiable programming, deep learning. So you can actually endow any deep neural network with an associated Gaussian process posterior by taking the deep neural network first, training it in any which way you like. That's step number 1. When you do that, you minimize an empirical risk, typically a regularized empirical risk, but you don't even necessarily need a regularizer. You just find the mode of the loss. Then at the mode, we make the mental assumption that we can linearize the network, the deep neural network F, which is a bivariate function of inputs and its weights, as an evaluation of that function with a fixed set of parameters, namely the trained weights. That's still a function of the inputs. That's your trained deep neural network, plus its Jacobian with respect to the weights times a residual to the trained weights, which we can think of as a feature map created by the network using automatic differentiation. That's just a conceptual step. We don't actually implement anything yet, but we realize that this function we have, it's called the trained network, and this function we can easily get in a deep learning framework because it's just the thing you need to do gradient descent, the backward pass, basically. Then you do a Laplace approximation in the way I just described. If you do this, then actually this Hessian simplifies a bit. It gets a more restricted structure that's nasty to write down and also sometimes nasty to implement, but it's easier to do than the full Hessian. And the Laplace approximation gives us a Gaussian distribution over the parameters. So now the last thing we need to do is to marginalize out those Gaussian distributions on the parameter space, on the weights, using this linearization assumption for the network. And these 4 steps together tell us that we actually have a Gaussian process posterior associated with our trained neural network. I still find this a very interesting perspective, is precisely because it is so simple. So there are other ways of adding uncertainty to deep learning that tend to be more costly and less direct. This is a very, maybe it's perhaps a somewhat daring thing to do because it's a very local approximation, right? It might just be a very bad approximation to the posterior because it only takes the local shape into account. But it provides us with very tractable and very interesting structures that I recommend anyone doing deep learning should have at the back of their mind just to analyze their model. If you train a deep neural network, you can think of a Gaussian process that you have constructed that has a mean function given by the network you just trained, and a covariance function, a kernel, that involves these green objects, which are the feature functions of your network, the Jacobians at the trained point, and this red thing, this inverse covariance, inverse Hessian, inverse curvature matrix of the loss at theta star, which is the bit of this framework that brings the data into the uncertainty quantification because it contains the loss on the training data. So these are data structures that you can think of as representing the data set, so the knowledge extracted from the data set, its relationship to the function we're operating on, that's these features, and then centered on the predictions that the network already does. And I did a whole lecture on like trying to argue that this kind of functionality is practically useful, that you can use it to do things like retrain, parameter efficient fine-tuning, visualization of uncertainty, explainable machine learning, and so on and so on. Okay, now we're getting towards the more final parts of the lecture, but there's a question first. You're asking a very good question. So for this to work, this matrix has to be positive definite. And you're right that in general, this Hessian may not be positive definite. So if we do this linearization, then this red matrix actually is positive definite by construction. So that's a nice aspect of this. That means at least you know that the thing you get will be a Gaussian process and it won't be nasty behaved. But of course, it might miss some important bits that come from this linearization, so that we're basically dropping some higher order terms in F. And in fact, it may well be in the future an interesting thing to study. Because what does it mean to have a Hessian that's not positive definite? It means you're not actually at a minimum. Right? There's a direction along which you can change your network, and either you don't change anything, then it is invariant in some direction. That's, I think, a very common known aspect of deep learning. Or, in fact, you're at a saddle point, and then there's a direction to take along which the loss will go down. And then it might be good to know about this, right? So, yeah, totally good point. But I think it's not a problem of the probabilistic interpretation. It's just the general aspect of deep learning that we're posing non-convex optimization problems. And then we inherit problems like this. Okay, so that was the uncertainty quantification for deep learning part. Now I'm going to quickly do the final few things, which were admittedly a bit of a ragtag collection of things that I felt like I have to do in a probabilistic machine learning class. The first one was sampling methods. So sampling methods are algorithms that use random numbers. I started by pointing out that we often need expected values in statistical inference, Bayesian inference, and in statistical inference. So such expected values can actually be approximated using what's called the Monte Carlo estimate. And what this is a sum over finitely many evaluations of the function whose expectation we're trying to construct, using evaluation points that are IID samples from the distribution P. And I put IID samples in quotation marks because I did a big spiel for a whole 90-minute lecture that confused some of you, and some of you kind of liked it, to point out that this idea of IID randomness is very flawed as a concept. In fact, it relies on things that fundamentally cannot be computed, which are then approximated with things that aren't actually random, and it's all a bit weird. Nevertheless, this use of these pseudo-random numbers has become very common in machine learning, and we do it all the time, even though, and actually we tend to do it in a totally deterministic fashion, using fixed random keys so that we can run the code several times and it produces the same plot every time. So there isn't actually any randomness, but whatever. And this philosophical problem also actually carries over into the analysis of these methods. There is a classic argument that Monte Carlo estimates are in some sense optimal because they achieve the optimal convergence rate of an unbiased estimator, the Cramer-Rao bound. However, that bound is fundamentally already using the idea of randomness. So it turns out that, at least for some problems, there are actually estimates that you could call biased if you like, but it's not really a concept that makes much sense if you're using a deterministic quantity that converge much, much faster. Nevertheless, I don't want you to think that Monte Carlo methods are completely stupid or shouldn't be used. I'm using sampling methods in some of my work as well. They're just sometimes very convenient. Maybe in your head, you can think of Monte Carlo methods as algorithms that are the first thing you might want to try, but the last thing you should actually do. By which I mean that they can be very easy to implement. Often they just need access to P, an unnormalized probability density function, which is often easy to evaluate. For example, if you can just multiply some prior with some likelihood, no matter what the likelihood and the prior is, you have these objects, and then you can just call these methods and let them run. And then they tend to provide samples that converge reasonably quickly. They're often easy to implement for, in particular, quite unstructured problems where you just don't know what to do elsewise. We encountered several such methods, like, well, first of all, the basic method that just uses direct samples from a distribution, that's sometimes called simple Monte Carlo. And then algorithms that are more approximate, like rejection sampling, importance sampling, all sorts of Markov chain Monte Carlo methods, like the basic class, Metropolis-Hastings, Gibbs sampling, Hamiltonian Monte Carlo, Langevin Monte Carlo, and so on, which are all increasingly complicated approximations that only asymptotically actually draw IID from the distribution. Nevertheless, these are easy to implement, and then they quickly provide a bunch of numbers that give a rough estimate, 1 over square root of number of samples convergence, for the thing you're trying to estimate. And if that's what you're going for, that's good. If you want to have a highly performant algorithm that can run on large data sets or on many, many instances of the same problem, something else might be a better idea. Talking about something else, I then, because I was talking about random numbers already, had a lecture on generative models, on diffusion and flow matching models, which are now the state of the art at the moment for the generation of natural images. And everyone has used one of them probably already, so we were interested together in how they worked. And one way to address them, as I argued back then, is from the sampling perspective. We may discover that sampling from a complicated distribution over some variable x0 is hard, even for very good sampling methods like advanced Markov chain Monte Carlo methods. Where complicated might mean, but doesn't have to mean, that the distribution has islands. It only has a few points on which it has non-zero mass. It might also mean that it spans some kind of manifold that is very slim within the space parameterized by your x that you'd like to sample from. In such situations, one operation that is quite interesting, that is not part of classic Markov chain Monte Carlo methods, is to take the distribution over x0 and convolve it with a Gaussian. So that means we create a new random variable y, which is the old random variable x0 plus Gaussian noise. When we do that, the new variable y tends to have a distribution that is easier because it looks a bit more Gaussian. So it's easier to draw from. It's a bit wider, it's a bit less isolated with islands. And what we can do is we can let our Monte Carlo method operate in this more noisy space, more regular space, and then take a step and estimate what the corresponding x0 is by trying to invert the noising process, by denoising the sample. Now we notice that this isn't, like, this is a bit of a zero-sum game, because the more noise you add, the easier you make the distribution to draw from, but the harder you make the estimation process. So the really cool idea is to say, maybe we just don't do one noisy step, but we take a continuum, or at least a large number of small noise steps that go from the original sample to something that can be considered basically a standard Gaussian distribution. And then instead of doing a single estimation step backwards, we do a whole long sequential denoising process. Because then every individual estimation step might actually work quite well, because the local noise is very small. And to do that, we need access to a model that can guess the noise, basically. And we discovered that that's related to estimating the score of the, this noising distribution at any point in time, t. And that can be learned, for example, with some deep neural network, which I showed a simple, very simple example for. And of course, now there are very elaborate such models that can generate really powerful sampling algorithms that can sample from basically the manifold of natural images, even conditional on some word description of what should be in the image. There's a continuous limit of this that actually is what a noise process is, a stochastic differential equation. And that backward denoising process follows the score of the probability distribution, which can also be phrased in terms of an ordinary differential equation without noise, where you basically just draw samples once, and then the dynamics of the entire set of samples follows an ODE. That's called the probability flow. And such models that use this ODE are called flow matching models and are now maybe the state of the art at the moment, at least, at the point of talking for generation of samples from complicated distributions. Okay, that was the generative modeling part, and there's questions for that. Say again, shouldn't, oh, is the verb wrong? What?
We say it becomes harder as alpha increases in the second point.
Ah, as alpha, yes, decreases. I'm sorry, you're right. So as alpha decreases, we get closer to a standard Gaussian, right? This becomes a 1, this becomes a 0. Yeah, you're right. Yeah. Okay, so now in the very final 3 lectures of term, I introduced another concept for approximate inference, which is historically very important and continues to be used today in many applications, often for analytical purposes, but has become maybe less prominent than it was a while ago. And so I'm myself also a bit uncertain about how much I should teach about it. So I ended up investing, well, 2.5 lectures into it. And we started getting to this framework called variational inference by first studying an even more classic algorithm called EM. EM is a quite specific algorithm for finding maximum likelihood estimates in cases where the likelihood itself of the data, the marginal likelihood, is hard to evaluate, but can be made easy to evaluate if we add latent variables Z. So this object, without the integral around it, just this inside here, is called the complete data log likelihood. For example, we saw that this shows up in Gaussian mixture models, or in general in mixture models, actually. In mixture models, this Z tends to be the variable that tells us which datum belongs to which mixture component, and then everything becomes easily tractable. This algorithm consists of 2 steps that get iterated. In the first one, we set a distribution over Z to the posterior over Z given X at a particular point in the parameter space. And we can think of this as a sort of very important look ahead into variational inference as constructing an approximation to the posterior at the correct value theta that happens to have the property that it minimizes the KL divergence to the posterior at the current point in the parameter space theta. And then, in a second step, the so-called maximization step, we change the parameters. So in the estimation step, in E, we estimate the latent variable Z, and then in the maximization step, we change theta. We change the parameters to maximize this expression, which is the expected complete data log likelihood, an expectation under the posterior over the logarithm of the complete log data, likelihood plus a constant, which is the entropy of Q. And so we found that this object, which we maximize, is called the evidence lower bound, because it is a lower bound to the evidence. So the evidence is this thing, and the difference between this thing and the evidence is a positive number, the KL divergence between our approximation and the true posterior. So by setting locally at a particular point in theta Q to this posterior, we're making this 0, this bound becomes tight, and when we maximize it for theta, we have to also increase this value. And so we found an algorithm for maximizing this likelihood without ever actually evaluating this likelihood, which is kind of cool. So now the next step, the final step for variational inference, is to say, maybe I can get away without setting this bound to exactly this, so without making this KL divergence 0, but just by trying to increase this object and thereby minimizing this object, because this is a constant. Right? So in terms of Z, at least, right? So when we try to maximize this, we will find a Q of Z that gets as close as possible to the posterior. And we can think of that as an approximate inference method for finding distributions that are good approximations to the posterior. And these are called variational inference methods. Why? Because they vary an object Q that is a function. They are optimization algorithms that operate in the spaces of functions, actually in the spaces of probability distributions Q, rather than optimizing in Z to find modes of distributions and then describing them locally in terms of Z, like Laplace approximations did. But how do you quantify the space of distributions over which you want to optimize? Well, an easy thing is that you could just you could decide that Q of Z should be some parametric family, like it should be a Gaussian, for example. Then you can just optimize the elbow directly. Okay, fine. Maybe you want to do some integrals, this integral in there using Monte Carlo. That's called fixed form variational inference. But there's actually a less restrictive form that often is surprisingly possible to do, that only imposes a little bit of algebraic structure on Q. And this is called the mean field assumption. So we assume that our Q of Z, which we want to be a good approximation to the true posterior on Z, has to factorize along some set of variables. If we do that, then it turns out that the evidence lower bound, the elbow, can be written as an expected value. So the evidence lower bound as a function of one particular of these variables, Zj, can be written as an expected value of the log complete theta log likelihood under expectations over the other variables. And because this is a function of Zj, even if we don't know how to do this integral, we tend to be able to see from the functional form of a generative model what the functional form of our approximation should be. And then if we do that iteratively across all the variables, we are often able to do the individual expectations because they become, for example, exponential families for which we know how to do the expectations. And that leads to iterative algorithms that can sometimes be very efficient at constructing like algorithmically efficient and distributions of high quality for approximate inference. Doing that requires writing down a lot of equations on a piece of paper, doing some analysis for ourselves, which is maybe like a last holdout of human labor in the times of AI. And then on Tuesday, I told you that this kind of framework, if it's applied to mixture models, can be thought of as having something to do vaguely with attention, maybe mostly just to motivate you to have a look. With that, I'm through term, but I'm not completely done. I have like 2 minutes left. I'd like to summarize on a very high level what I was trying to get across for this. This is for many of you one of the two or three key lectures in your master's degree on AI and machine learning and computer science. I wanted to endow you with basic understanding for the relationships between model classes, the functionality that is available in machine learning, and how to think about it. Not so much just about implementation. Of course, we did that as well. I wanted to convince you that probability theory as a mathematical framework provides the foundation and the framework for the design of machine learning methods, because it formalizes the process of extracting information from all sorts of information, and that might be empirical data, but it may also be mechanistic knowledge, like knowing that there's a differential equation that drives the system, or computational information, like knowing that you have evaluated the gradient of a vector field a bunch of times, and now you know a little bit about the vector field, but not about the entire thing. And because the mechanism of probabilistic inference is fundamentally intractable, it requires us always to do approximations. Sometimes someone asked last week, isn't that a problem, that we always have to do these approximations? Everything always ends up Gaussian in your lecture. Why can we even trust this? Well, it turns out that everyone in science has been doing this for at least the last 2 centuries, including Newton and Einstein and other people who probably really knew better than most others, because you don't get around writing down, like making approximations. If you want to write down something, you can actually do, either on a piece of paper or on a computer. And so all of, including modern machine learning, is a form of approximation. The probabilistic perspective just allows us to reflect on this better. And of course, there are powerful mechanisms like the ones we discussed today and over the course of the term that actually work, that you can actually apply. And they allow you to get insights either to build real tools like the Gaussian process models we build or these exponential family models we build, or of course, diffusion models. But sometimes they also help us get insights, like this story about deep learning, this differential geometry perspective on deep neural networks that allows us to identify new functionality for existing models. So for example, in deep learning, there are classes of methods that were invented in a way that had nothing to do with Bayesian inference. But now that we think about them as Bayesian models, we discover that we can use these insights to create new functionality, like continuous learning, for example. That's what I wanted to say at the end. Now I'm 1 minute over time. If you have more questions, you can also come to the front. I'm grateful that you were here all the term. And I'm looking forward to see many of you on Monday at 8 a.m. for the exam. Thank you very much.